Hello all. This is a lecture concerning resistance and voltage and current. This is basically everything we went over on September 14th and 15th. That's a Thursday and a Friday of last week. So let's go ahead and get started. So if you recall from the last lecture, we were talking about voltage and current, and we have determined that the more voltage we have, the faster the current will go. So let me write that down. So voltage and then I'm going to put down current right here. And current, of course, has two R's. All right. So now I can draw some arrows. So as voltage goes up, current also goes up. So voltage causes the current to go up. So what if current goes up? Does that mean voltage went up? Well, if we change nothing else, it does. So it goes both ways. There is a name for something like that, and we can say that voltage is directly proportional to current. Okay. So what I'm trying to do right now really is to make some nice mathematical equation that will tie voltage and current. Unfortunately, just this relationship alone is not enough to give us a nice formula to use, because there is something else that we need to use, and that something else is called resistance. When you think about resistance, you can think of it as friction, if you will. You know that if you're trying to slide something on the floor, you have friction. That's what stops the object. That's why if you have rollerblades, for example, they have less friction, so you can go a little farther. So the same deal happens in the wire, and in general, there is something that tries to slow down the electrical current, and that is something called resistance, and you can think of it as some kind of friction that slows down the electrons. So let me put down a few key points. So the very first key point, resistance slows down the current. And you can think of resistance as friction. In that regard. Friction is actually a really complicated thing if you study it and try to make some nice wheels and tires that have a lot of grip. Resistance is a lot simpler than that, believe it or not. So resistance slows down the current, and the relationship we now have is a rather reverse one. So as resistance goes up, my current actually is going to slow down. So let me get my arrows. Resistance goes up, current goes down. And if we change nothing else, if the current goes down and we still have the same voltage, that means the resistance went up. So it also goes both ways. So before we derive that final formula for resistance, I do want to give you the proper textbook definition of resistance. And that one is really nice, even though it does sound a little weird at first. And it reads like this: resistance is a measure of opposition to the current. Now that is a bit of a mouthful, and it doesn't really make a lot of sense the first time around, but it actually is very, very, very straightforward. This is what it means. I'm going to put explanation here. First of all, we already know that resistance resists the current. Well, opposition is resistance. So when it says resistance opposes the current, we're just saying resistance resists. But that's why it's called resistance, right? That's pretty straightforward. Now, the second part of it is actually this word measure right here. And that is important because it doesn't just resist the current. It resists it in a particular way that is measurable. Now, not every single time you can measure something. Every once in a while, you can have quantities that are not measurable. But in resistance, it works like this. Every single time you have a resistor, it's going to resist in exactly the same way every single electron that passes through it. It's not going to go like this. Oh, well, this electron, he's my friend. I'm just going to let him pass free. But this electron, I really hate him, so I'm going to really resist him. That's not how it works. It passes all the electrons the same way and resists them about as much and slows them down by the same amount, which means that amount is measurable. So well, if it's measurable, then we have to have units. And units for resistance are ohms. And this is how you usually write the symbol for ohm. Ohm is the capital letter omega. So this is my capital letter omega. So now I'm finally ready to derive my formula. So if you remember, we had voltage directly proportional to the current. Now resistance, look, we have resistance going up, current going down. That is also some kind of proportionality. So I'm just going to put this down here. And that actually means the resistance is inversely proportional. Directly proportional is when you increase one thing and the other thing also increases. Inversely, you increase one thing, but the other one decreases. So resistance is inversely proportional. Okay. And let me arrange this real quick. There we go. Much better. Okay, so inversely proportional, directly proportional really does mean something in terms of our formulas. So for directly proportional, it literally means in the numerator. So as current goes up, voltage goes up. Inversely proportional means in the denominator. And now we can put an equal sign. This is something called Ohm's law. And we're going to use it a lot in this class. So this is the end of this lecture. I'm going to put up another lecture on how to actually use the Ohm's law and how to use the Ohm's law triangle next.